In this section, we're going to just do an overview of some of the properties of gases and what we know about some of the gas laws that will determine what kind of the properties different gases will have. Gases are a little different than solids or liquids because they offer little physical resistance when you are kind of going to push on them. They have a lot of space in between the molecules, and therefore generally there are a lot less intermolecular forces that are involved or interactions between the different molecules. They typically are moving at pretty high speeds because they have a lot of kinetic energy. Generally they have to have that in order to be released from a liquid, for example, or a solid, and they're going to collide with the edges of whatever environment they're in, and as the temperature increases, those gain kinetic energy. So that's the translational energy, which is the movement, vibrational, and rotational energies that have the capacity to have all of those different types of kinetic movements associated with them. Despite different chemical properties, for gases, they generally observe and obey a set of physical properties that we'll define in this section. So the four of them are generally going to be pressure, volume, temperature, and the number of moles. We're going to be looking at those four physical properties and how they relate to each other in gases. So first, just to define some terms, I want to talk to you about pressure. And that is the idea that we have a certain amount of force on a specific amount of area. So pressure is a force per unit area. So we'll talk about some of the ways that we measure this. But an example of this is Earth's gravitational force. So anything that has mass near it. Weight, again, is the force that the Earth is going to exert on an object with mass. What we call weight is actually gravitational force acting on an object. So here's an example of a wooden floor, maybe if you're stepping on it with pointy heels or something, and we're going to look at flat shoes versus high heel shoes and the difference in force that those shoes are going to put on the ground. So if we have a woman that weighs 120 pounds and we have the different flat shoes versus high heels, the area of the shoe, right, if they're flats, the shoe surface is going to touch that whole floor area about 10 inches times 3 inches in 10 inches long, 3 inches wide, and that's 30 inches squared. So that's the area versus high heels where you have a lot smaller footprint, and the overall area for where it's touching the ground is 0.16 inches squared versus 30. So if we take the pressure, as I mentioned before, it's the amount of weight, for example, over the amount of area. So we have 120 pounds. It's the same person, just in two different shoes. One that has the flats of their feet on 30 inches squared versus 0.16 inches squared. And we have 4 psi versus 750 psi. So pounds per square inch is psi. So the pounds per inch squared, that's where that term is coming from. So you have 4 psi if you have flat shoes versus 750 psi versus high heels. So you might do some damage to the wood, for example, if you have different types of shoes, and that is just kind of showing you and describing what that pressure means. You can think of pressure differently also in terms of where we are in altitude. The more pressure, the closer you are to Earth, the more heavily there are going to be more elements and compounds and gases are going to be more dense in this area. So as you change your altitude, you're going to change the pressure at which you are kind of sitting under all of these molecules. Earth's gravity is still acting on the molecules of the air, and that's a lot of what we see when we look at the weather. We look at high pressure, low pressure. That's going to change the amount of stuff in the air, and that's going to tell us something about the weather patterns that are going to happen. A lot of times we're looking at barometers, and those are used to measure different atmospheric pressures. And they work by basically having, and you don't have to use mercury, you could use other things, but you use something that's calibrated, a piece of glass, And basically that air pressure, as it changes, it's going to put more pressure on this liquid. If it's mercury, for example, that's going to flow up this tube. And these are going to be graduated. So there'll be little spots on here, how many inches up that tube that mercury is going to flow. And as that happens, this is in a vacuum, so there's nothing in here. So the mercury can move up here freely depending on that pressure. And so a lot of times this is kind of a really simple barometer, typically about 80 centimeters in length and sealed at one end. And you'll have millimeters of or centimeters of mercury, or whatever that measurement is. That's going to be a certain type of pressure readout. If you were to take that device at sea level, you would see that the readout for that barometer is going to be 760 millimeters of mercury. So that's a standardized measurement reading. If we go on the top of Mount Everest, that's going to drop to 250 millimeters of mercury. So we drop that pressure depending on where we are compared to sea level. Because as I mentioned before, down at sea level, you have a lot more components and things that are pushing down on you versus at the top of Mount Everest. You have less molecules of gas pushing down at you on Mount Everest versus at sea level. So there are various different types of units of pressure. 1 atmosphere is the typical average number of, the pressure at sea level. And that is equivalent to about 100,000 pascals. So that's a very small measurement. And then you can also sometimes see that in kilopascals. Other units of measure that, atmospheres are usually too big for most labs to work in. So you're not going to use 1, 2, 3 atmospheres, but this is a good measurement if we're looking at planetary pressures, for example. If you go to Mercury, how many atmospheres of pressure would you have on you if you were in Mercury versus the Earth, right? That might be a better measurement for larger scale things. So this is also bars is another measurement. And millimeters of mercury we also mentioned. So that's about 760 millimeters of mercury is equivalent to 1 atmosphere. Torr is another equivalence to mercury as well. So typically at sea level, 1 torr is equal to 1 millimeter of mercury. So it depends, this value changes depending on where you're at. Now that we've introduced this idea of pressure and what it means and how it's measured, I would like to talk to you about now looking at relationships between some of the pressure, volume, temperature, number of moles. And one of them is Boyle's law. And this one looks at the difference between pressure and volume. So if I have gas in a cylinder and I have a piston and I'm able to compress this down into a smaller volume, what happens to that pressure? And Boyle's law describes that as we compress this down, the amount of pressure is going to increase. So volume decreases, pressure increases. And this should make kind of sense. Obviously, we're going to keep the number of moles of things the same, and we're not changing the temperature. We just want to change the volume at which those gas molecules have. And so this is kind of Boyle's law. It's found that when we decrease the volume, we increase the pressure. Another law related to gases is Charles' law, and we're looking at the volume versus the temperature. So here you can kind of see from this, if we keep the pressure and the number of moles constant, so we're not allowing the pressure to change, we're not changing the number of moles. As we increase the temperature, we're increasing the volume of that gas. And the last one I want to look at is Gay-Lussac's law, where we're looking at volume and the number of moles when those are constant. And we're going to look at the pressure versus the temperature. So if we have the same number of volume and the same number of moles, but we increase the temperature, we see that the pressure also increases. So pressure and temperature are intimately related in these gas laws. And as, again, just this chart, as the temperature increases, we also see the pressure is going to increase. Another principle we're going to look at is Avogadro's principle. And this idea, if we're measuring at the same temperature and pressure, and we're looking at equal volumes of gas, those volumes of gas will contain an equal number of moles. And this is kind of related to all of these things. We're going to combine these ideas in a moment, but it's the volume of gas is going to be directly proportional to the number of moles, and where the volume is proportional to moles at constant pressure and temperature. So the idea here is that if I have 1 mole of hydrogen, 1 mole of chlorine gas, and I then make 2 moles of HCl, these volumes should be similar. The number of moles should be similar, and that's kind of what we're describing down below. So we have 2 number of volumes, we have 2 molecules, we have 2 moles on the left combined, and then in the right, these are all also equal to 2. So this is Avogadro's principle, and we're going to now look at all of these things combined. How does this work out? So this is the combined ideal gas law. So we have components of all of those little laws that I was talking to you about, the Gay-Lussac's, Boyle's law, Charles' law, Avogadro's ideal, and we also have this constant, which is defined for each different the types of gases that we're going to be looking at. We also have a law that we're going to talk about, and this is where basically if we're looking at one gas, then anything, if we want to determine in that system, maybe we have a number of moles, or we have a volume, or we're missing a temperature. We can, if we have 3 of these, and then we'd have the constant. We'll talk about that in a moment. You'd be able to solve one of these other ones. Or if you have something that's changing in a system, so you have a 1, which means maybe a reactant, and then your product, for example. If you start with everything's constant, but then you're changing the volume, or you're changing the temperature, you'll be able to plug in the numbers and then solve one of these if you don't know them. So these are a couple of laws that are useful for solving problems regarding gases. So this ideal gas law, this is a little different than what I showed you on the previous slide. PV over T is equal to C. This is a constant for specific types of gas. And this is going to be, if we go back one slide, you can see this PV over T is a constant. That one's kind of has Avogadro's number in a different spot here. And I'll show you here with the result, it would actually be PV over T times N times this new constant. So that other slide, this was a K, and then the N was actually divided over here. So we're just moving things around. But this is a good universal gas law. PV equals nRT. And this is what is commonly used. This is a little bit easier to work with than the previous version I showed you on the other slide. This is what most people will use to solve problems. If you have maybe a couple of these, or if you have some of this information but not all of it, in order to solve it, this is a good one to use. So again, when we're looking at different types of gas laws, we have the ideal gas law with PV equals nRT. So if we have something, if we're defining terms, nothing's really changing between the reaction. We just need to know, I don't know what the temperature is going to be at, or I don't know how many moles, I don't know the volume, I don't know the pressure. We can solve for this. And I'm going to talk about this constant in a second. However, if we're looking at the combined gas law, this form is helpful if things are changing, right? If I'm changing the volume, or I'm changing the temperature, changing the number of moles during a chemical reaction, for example, then this would be the version of that ideal gas law that would be more useful than the one over here. So 2 different types of equations we can use for different sets of types of problems. And now I want to talk to you about that gas law and the term, the R term, that constant here, and we'll talk about that. Just first, I want to talk about standard molar volume. So a volume of 1 mole of gas must be identical for all gases under the same temperature and pressure, and that's what that previous Avogadro's law was talking about. And then we have standard temperature and pressure, that's STP, for different conditions are going to be an atmosphere. So basically you're at the ocean level, and then 273.15 Kelvin, and that is 0 degrees Celsius. So these are standard temperature and pressure conditions. And under these conditions, 1 mole of gas occupies a volume of 22.4 liters. So these are ideal normal gases, and the volume is always going to be this at these standard temperatures and pressures. So this is the standard molar volume for any ideal gas. So in that equation, PV equals nRT, the R is an ideal gas constant, the universal ideal gas constant. And if we plug in values for TV, N, and P for 1 mole of gas at standard temperatures and pressure, which would be 1 atmosphere at 0 degrees Celsius, we can do that here. We know the volume is 22.4 liters, which I just spoke to you about. We can solve for R. We're going to solve for that PV equals nRT. We're going to rearrange this so we're solving for R. And we have the pressure is 1 atmosphere. The volume is 22.4 liters, which I just spoke about. The 1 mole, and at 273.15 Kelvin, that R is going to be 0.082057 liters atmospheres per mole per Kelvin. And that's the constant that we can plug in to solve these equations. So let's do an example of this. So let's look at, this is the ideal gas law, PV equals nRT. How many liters of nitrogen gas at 1 atmosphere and 25 degrees Celsius are produced by the decomposition of 150 grams of sodium nitride? So let's look at this problem, and we're going to figure out how many liters. So we need to identify a volume. I'm going to pull out the other information that is in this equation. The pressure, it's 1 atmosphere. The temperature is 25 degrees Celsius. I need to convert that to Kelvin, which I've done here. So it's 298.15 Kelvin. I'm going to solve the equation for volume here, which then gives me nRT divided by the pressure. So I have a volume is equal to nRT divided by pressure. And I'm going to start plugging and chugging some information in here. But first, I need to solve for the number of moles of nitrogen. And so the moles of nitrogen, I have 150 grams of this NaN3. And then I'm going to convert that so that I can get the number of moles. And here I have to use stoichiometry, where I have 1 mole of this NaN3 is going to give me 65.0 grams. So this is the molecular weight. 65 grams is equal to 1 mole. So that gets me from grams to moles. And now I need to use the coefficients to give me an equivalence between these compounds so that I can get my units of moles of N2 out. So the moles of N2 are going to be for every 3 moles of N2 gas, that's equivalent to 2 moles of NaN3 gas. That's down here. So 3:2 ratio based off of the coefficients. And then I can solve for that. Those grams cancel out. The moles of NaN3 cancel out. I'm left with moles of N2. So here I have 3.461 moles of N2. Now I have P, I can plug that in here. I have the temperature, I can plug that in here. I have N, I can plug that in here. And on the last slide, I mentioned that the R is equal to 0.082057 liters times atmospheres over moles times Kelvin. So I'm going to plug all those values into this equation. 3.461 moles. I have my gas constant here with the proper units. I have Kelvin that I identified here, and then I have 1 atmosphere of pressure. So the moles of N2 cancel out, my Kelvin cancels out, my atmospheres canceled out, and I'm left with liters. So that's a good sign that I have my proper units are left. And the volume of this is going to be 84.6 liters then. So that's an example of working through one of these. And this is more complicated, right? There are a number of different steps. I had to do a conversion. I had to use stoichiometry to solve for the thing that I actually wanted, right? I started with, 150 grams of my reactant, but I wanted to know what the products were going to be. So these are some of the kind of ways that we can use these gas laws to solve problems. Okay, I'd like you to try to do this now. What volume in milliliters does a sample of nitrogen with a mass of 0.245 grams occupy 21 degrees Celsius, 750 torr? So what do I know? Mass and identity with the molecular mass of the substance. So we should be able to find the number of moles. We have the temperature, we have the pressure, and I need to find the the milliliters here. So in order to solve this, we're going to, I don't know the volume in milliliters, that's what I want to know. I have the mass, and I know that the molecular mass for my compound is 28 grams per mole. I'm going to have to convert degrees Celsius to Kelvin. And so 21 degrees Celsius conversion for Kelvin is going to basically add 273.15 Kelvin. So that gives me 294 Kelvin. Convert pressure from torr to atmospheres, and 750 torr is 1 atmosphere is equal to 760. So I can cancel those units out, just under 1 atmosphere, and then convert mass to moles. So I have, for this compound, I have the number of mass. I have 0.245 grams. And I have, this is maybe a condensed way to do this. Probably a way that is better to show you actually would be, I have 245 grams of my compound. I'm going to then take that, and I have 28 grams over 1 mole. So that's the same thing that's essentially happening here, but it's laid out maybe in a better way that we've been talking about for using for conversions and factor label method. So this is the preferred way to show that. But in the end, we still get the same result. We get 8.75 times 10 to the negative 3 moles of compound. That's not a volume yet, so now I have to do a little bit more work. Again, the volume, PV equals nRT. That is the starting point. I've solved for volume, so I've taken the P, I've divided that group by P, and so I've solved for volume. And the next step is to plug all those values that I just defined in, right? 8.75 times 10 to the negative third is what I figured out for the number of moles. We have liters, atmospheres per mole per Kelvin. This is just the R is the gas constant, and we have 294 Kelvin, 0.987 atmospheres. So the units of moles cancel out. Moles here, this is negative 1 mole, just means it's in the denominator. This is just a different way of showing that same idea. These negative 1, remember, in the denominator, so these will cancel out. Our atmospheres are going to cancel out next because those are in the numerator versus the denominator. And then we have liters on top. So that's going to give us the liter unit out. I said I wanted the answer in milliliters, so I'm going to do a quick conversion. And then I have 214 milliliters. Okay, so I want you to try one of these things. I want you to tell me which of these 3 and post this answer in our Blackboard space. And then hopefully, if you have any questions about how to solve this or which was the correct answer, then we'll discuss that in our Blackboard space. But use those gas laws to solve this problem. Okay, great. So I just spent 20 minutes talking to you about gas laws for ideal gases. However, real gases typically deviate a little bit from the ideal gas law. So we have the PV equals nRT. Why do these actually differ? So if we're looking at something like oxygen, we have the pressure and volume over temperature. We're looking at the atmospheric pressure. And if we're looking at what an ideal we'd expect from an ideal gas, this is the green line here versus what actually happens with something like oxygen. Gas molecules have finite volumes, so they take up some amount of space. They can't be pressurized infinitely, right? They have to take up some amount of space. So you can't just keep increasing the pressure. They still have some space they have to take up no matter what. And so that's going to have to increase at some point, as you can see with oxygen. The less space that you have as you keep pressing those together, we change the kinetic motion that's happening. And you also have something to do in the container, that the motion in there is reflective of what kind of container that you're putting it in. So they hit the walls, the wall hit the edges more often as you pressure that down. So that changes some of the characteristics and some of the kinetic energy that that system has, and it will get converted into whatever that walls of the container are as well. So here pressure is higher compared to ideal because of these different types of things. Part of the also reason that we have differences in ideal gases versus real gases is that they are going to have some intermolecular interactions with each other. As they diffuse and as they move through a room, for example, ideal gases, we would say that they would just kind of move independently from each other. They don't interact in any way and they disregard each other. However, in real gases, when things get close to each other, they'll actually change the trajectory of where they're going in the container. They'll interact with each other a little bit, and we have changes in the pressures and the kinetic energy and the directions of which they're interacting. And these little stars here, every time they interact, that's changing the energetics of that system a little bit. So they do attract each other, even if they're weak attractions. It means they hit the walls of the containers maybe a little less often, and the pressure, for example, might be less than in an ideal gas. So if we have a lot of these compounds in a solution, or sorry, in a gas phase, but they're interacting with each other a lot, or there's a high pressure, or there are a lot of them in this container, the more of this that will happen. So we get further away from the ideal range. And we've spoken about van der Waals forces, and this is the equation that helps to correct some of these assumptions based off of ideal gas laws. So we have corrected pressure, where we're changing some of these terms. For A and B, they're basically van der Waals constants. So A here and B here, where we're correcting the pressure based off of those interactions for various compounds, and B here, correcting the volume. And so these are going to be basically figured out and obtained by measuring the pressure and volume and temperature for real gases over various ranges of conditions to see how they change based off of or compared to the ideal gas law. Here we look at the pressure correction, and it indicates that there are attractions between molecules, between large molecules. And if you have a small a versus a big A, it's looking at there's a strong attractive force versus a weak attractive force. So we're looking at attractive forces here. If we're looking at B, the correction for B, it's looking at the size of the molecule. So if you have a really big B, that means you have a large molecule. You have a small B, it means you have a small molecule. So if we have gases that are most easily liquefied, have the largest van der Waals constants, which means that they are going to be able to attract each other and condense into a liquid. All right, for this now, I'd like you to kind of look at this question, and I'd like you to determine which is the correct answer. What I'm going to show you a few multiple choice options below. So if you have a given sample of gas, under which conditions our actual pressure is likely to deviate the most from pressures calculated based on the ideal gas law. So thinking about the equation here with van der Waals and what is being corrected. And if we're looking at, these are your options. So select the one that you believe is correct, post that in our Blackboard space, and we'll talk about the answers if you have questions. So that's a brief, quick overview of gases, and I think it's going to be about what you would maybe need to know just to kind of get started and just have a general idea of gases. And that is where we're going to finish up today. So thank you for watching the video, and let me know if you have any questions about these gas laws.